Okay, so today we're going to introduce the magnetic field, and we're going to review for the exam. And I came up with these brilliant, if I do say so myself, practice problems for us to do. And I'm worried I won't get to them all, so we're going to review first. So someday when Rice is asking you for money, remember that I reviewed first and then did the magnetic field. So if we're going to run out of time for something, we're going to run out of time for the magnetic field and not the review. But what about bioelectricity? Oh my fucking God. Are you fucking kidding me? No magnetic field and fucking bioelectricity. Electricity is not on the exam. There you go. There you go. The exam has one question when we say a teeny capacitor. And in parentheses, we had like a cell. And I erased that because I was worried people would freak out. It's like a cell. Oh my God. So I took that out. So bioelectricity is not on the exam. There's a capacitor with sizes similar to a cell, if you're paying attention. But it's technically not a bioelectricity problem. Okay, our review is off to an excellent start. Not even looking at my phone right now. Okay, here we go. So, review. So, my advice on review, actually, I think the equation sheet is better, maybe even than the list of skills, especially because it's complete. So, I think looking through the equation sheet and saying, do I really know what all these things mean? I mean, I could look these up, but do I know what P is? Do I know delta V where? What does delta V mean? Between 2 points and 2 points in time? You know, looking at those and making sure you know roughly what they mean is a good idea. Do you know about non-uniform electric field? Yes, the electric field from a point charge is a non-uniform electric field. So of course you do. Remember, the only fields we did is point charge, a uniform field, and then we talked a little bit about the dipole field along two axes, which I'm going to get to. Okay, so I like to just walk through that and say, do I understand all those? But also keep in mind that there are questions that are not on there. There are facts that you have to know, believe it or not, that are not on that sheet. Like how charge behaves in a metal and an insulator. Remember, that was the first how we start electrostatics is how charge moves around, how we generate charge, and there's no equation for that. You just have to know that. You have to know that charge sticks to the surface of an insulator, and charge can move around in a metal. Will you upload a key to the practice exam? No, we don't have one. We don't have time to make one. I can't make a key real fast. If I make a key real fast, we'll have mistakes. So I published an exam solution with mistakes right before the exam. It leads to a nightmare. So no. If you have a specific one you want to know about, come to office hours. But there is no time to make a key. Okay, so here's an example problem. 2 small, neutral, metal spheres, and these notes are already online if you want to look at them, near a charge. If you don't want to write these down and just go to Canvas, you could look at that. You got 2 small metal spheres near a charge of big Q. Right? So big charge sitting there stationary. You got a small metal sphere here, we'll call it A, and a small metal sphere here, we'll call it B. Right? Do they feel forces? Feel forces. And if so, hint, they do. If so, which is larger? Right, so there's an example of a question about how materials behave in an electric field, which is not really on the equation sheet, is it? So I'm not going to give you guys like 5 minutes to work on it on your own, or we'll never get through them. But you can think about it on your own for a second. Will they feel forces? Yes, this is getting back to that polarization idea. Even though these are neutral, remember, what is it that happens to a conductor in a non-uniform electric field? All right, so big field here. Doesn't matter that it's non-uniform. The little electrons will be attracted, so you'll get a negative charge, but it was neutral, so it must have been positive on that side. So sure enough, you'll get a polarization of the conductor. And then we talk about, does that lead to a force? It does, because it's a non-uniform electric field. You realize these are attracted to this charge, but they're closer. Right? So they feel a force this way. These feel a repulsive force. But it's smaller because they're farther away, because it's a non-uniform electric field. So the net force on this one is attractive. And you may remember we said that a neutral conductor is always attracted to a charged object. And this is why. Is because it will be pulled. Well, not always. It depends on the nature of the field. A neutral conductor is always attracted to a point charge because the non-uniform field will pull it to the left. Okay? So the answer first is, yeah, they feel forces. This one also the same thing. But then which one is larger? That's a little harder, right? You might intuitively guess the one that's closer, it's going to be larger, and you'd be right. But if you really wanted to make sure you knew why, you could say, well, it's also going to get polarized. And then you might say, well, maybe it would get less polarized because the field's smaller, but we didn't really talk about that. So for now, let's pretend they get the same polarized. The answer is, yeah, it would also get less polarized. But let's pretend it's the same charge on both sides. Yet both forces are going to be smaller because they're farther away. Remember, the force goes as 1 over r squared. So this is smaller, this is smaller. There's still a net force this way, but it's going to be smaller than the net force this way. I mean, these aren't to scale, but you get the idea. So there's a mental jumping jacks thing you would have to do for a multiple choice. It's an example. It's kind of a hard multiple. That's not that hard. That's like a multiple choice. Oh, it's got 2 questions, though. Right? So that, nothing really on here is going to help you except maybe this. If you forget, oh, the force, how does it go with separation? We use this information, but you have to know a little bit about conductors and insulators to get it. 1 example problem down, 5 to go. All right. So there will be questions then about how charge moves in and around insulators and conductors. Everybody likes that one. All right. Nobody's asking questions because I keep screaming at you every time you ask a question. My strategy's working. 7, 1. The new people might ask a question, though. Yes. Okay. So you might be familiar with that. And then, okay, the one practice exam question I'm definitely planned on doing here is this one about what is the electric field where we have these 4 charges. So this is practice exam, and it's multiple choice 1. And it said you've got these 4 charges, minus, plus, minus, plus. Right? La 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 la. And they're separated by 2D. And if you're not sure why they did 2D, and this is the origin, then they're being nice to you by making it 2D. It makes the algebra easier. And they all have the same charge Q. So minus Q plus Q, minus Q plus Q. Right? And the question was, what's the electric field at the center? Or you could say at the origin. What's the electric field there? So I got one text about this question. They said, is it a certain answer because of symmetry? And symmetry could help you with this problem. Symmetry can often help you with these kinds of problems. We didn't do a lot of symmetry, so no offense, but you're not great at symmetry yet. Okay, you're good at it. You're getting there. But if you don't need to use, this one's pretty straightforward without symmetry. So let's do it first, and then we'll show you how symmetry could have helped, but how overuse of symmetry will destroy you. Okay? So one thing to remember is that electric fields superpose. Right? So the E at the origin is just the E due to 1 plus the E due to 2. I meant to label them 1, 2, 3, 4. 1, 2, 3, and 4. E due to 1 plus E due to 3 plus E due to 3 plus E due to 4. This is why you don't really need symmetry for this one. You can just add those up. Right? I mean, it's not that long here. So let's just start adding them up, and let's use a thing on the formula sheet. Right? E due to a point charge is very similar to Coulomb's law because we get it from Coulomb's law. K, the charge Q over the separation squared. So the tricky part of this problem is figure out what's the separation. 2D plus 1D is 3D over 3D squared. And you got to decide, what are you going to do with negative signs here? So, you can put the negative here and hope that it works out with your coordinate system. I would just always make the charge positive, put the charge magnitude there, and just define the direction, the negative or positive sign, with opposites attract. Or in this case, if it's a field, okay, a positive test charge here. So I would do this one by saying this way is positive. Right is positive, left is negative. Right? So in that case, the electric field due to a negative charge, it always points towards a negative charge. Because if I'm a little test charge here, I would fly that way. The force would be that way. So this one is actually negative. Right? And then let's do 2 plus. This one is KQ over D squared. And is it plus or minus? Test charge here, that way, it's plus. Right? D to the D, no. D squared. Right? Okay. Is the only way to make a uniform E field within parallel plate capacitor in this class? Yes. Why 3D? I don't know what you're talking about. Because we can't exist in 2D. The vector calculus doesn't work out. I don't know why there's 3Ds. Okay, this one. What's this one? Plus KQ over D squared. Right? KQ over D squared. Now, is this one positive or negative? This is why you don't want to stick signs in your charges. It will screw you later, right? If you put a negative Q here, oh, it must be this way. No. We're on its left side. If I put a test charge here, it's attracted that way. This gives you a positive field this way. Right? You can't trust doing this strictly Cartesian. You can't just put the sign of the charge in and think it's going to work out, because you're doing this on a Cartesian axis, and these are all spherical coordinates. So you actually do need to make this one plus. And then what about this one? KQ over 3D, the separation squared. 1, 2, 3D squared. And I think I just answered the 3D question. All right? Too far. This is 3D right here. The distance. It's over r squared, and that's the actual distance. Is this one plus or minus? It's minus. A little positive test charge due to this one would go this way. It would go negative. Electric fields point away from positive charges. So this would be minus. All right? So you say, let's combine the two that have a 9 in the denominator. Minus 2KQ over 9D squared. Those are the two minus ones. And then the two plus ones have a D in the denominator, plus 2KQ over D squared. All right? La 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 la. Then we've got a common denominator, yada yada. 9 is a common denominator. No, 18 is a common denominator. No, let's see. I can't do the math. D, I thought I made 20, the 19. This is 2 ninths and this is 2. So this is 18 ninths. Oh, yeah. And then this one's negative. So minus 2 ninths. Sorry. KQ over D squared plus, and yeah, this is 18 ninths. KQ over D squared. Right. So you get the answer. One of the answers is 16 ninths KQ over D squared. 16 ninths KQ over D squared was one of the multiple choice options. Why is the third term positive again? Third term is positive because I said this way is positive. So if I put a little positive test charge here, which way is it going to go due to charge 3? It's going to be attracted to charge 3 because opposites attract. Or you could say, for a point charge, the field points away from a positive charge and towards a negative charge. You could memorize that. Why is the first term negative? Same reason. Same reason. Yeah. So, remember, if I have a positive charge, the electric field points away from it. If I have a negative charge, the electric field points toward it. Or you can think of what a little test charge would do, either one. But these positive negatives are having to be assigned manually because it depends on what side of the charge you're on. That's what I'm saying. You have to manually think about them to put them in. Okay? 16 ninths is the answer you want. Okay? Now let's talk about symmetry. One brave soul said, I want to do this by symmetry. Isn't it just 0? Close. You can use symmetry here, but it's not 0. And the place you would want to use symmetry, I think, let's see. It's not 0. I don't know how else. Yeah. Okay. So the way if we wanted to think about using symmetry here is you could say, well, there's two pairs, right? There's a pair like this that make a field, and there's a pair like this that make a field. So you might be tempted to say it's 0 because those fields cancel, but they don't cancel, right? Because this point is close to these two, and it's far from these two. So it is true that this makes a field this way, this makes a field that way. But they don't cancel because they don't have the same magnitude. All right? I don't know of an arrangement that would give you a 0 here. Well, yeah, you could make a 0. You could have plus, minus. Well, that's not going to give you 0. Okay, I don't know how to make 0. It doesn't make 0. Okay. It's not 0 just because of that. If you add these two, you're going to get a field to the right. And sure enough, look, it's positive. It's a field to the right. The one way I came up with that you could use symmetry is, you could just write 2 terms instead of 4 terms. To use symmetry, you could recognize that these two are giving you the exact same number. They're the same distance. They're the same direction. So instead of writing this twice, we could have just immediately written minus 2kq over d squared plus over 3d squared plus 2kq over d squared. That's the only thing symmetry is going to give you in this problem. So we're not giving you lots of use of symmetry as critical problems because we really didn't do it that much, because we really didn't do field theory that much. I mean, we didn't do vector calculus that much. So if you're looking at some old 102 exam, then there's a lot more symmetry kind of problems. But we're not doing those as much. But if you see some symmetry that thinks it'll help you, then go for it. Man, we're burning through these things. Let's see. Okay, so then you might look at the old equation sheet here and say, oh, there is dipole moments on it. Yes, we are going to do dipole moments in the exam. It's the only way to make electrostatics interesting. Otherwise, it's just boring, simple plug and chug. Nobody wants that. Nobody wants boring, simple plug and chug. All right, so let's look at, I think we're done with that. Let's look at the dipoles. Can we always assume the test charge is positively charged? Yes. Test charges are always positively charged. Yes. Oh, smooth operator. Remember the dipoles. So this problem is called Remember the Dipoles. Sort of a problem and just some reminders. So a quick reminder that the dipole moment was this thing, a positive charge connected by a boba straw to a negative charge. Okay? So the two charges are stuck together. They could turn and they could translate together, but they're always separated by this little amount. Right, S, okay. S, right, that way, and P is QS. So you could say it's just the charge times the separation. Remember, it's this Q plus and this minus Q. It's not 2Q, it's just the charge of each. Right, P equals QS. But we all wanted simple plug and chug. Oh, future Trump voters. All right, cool, let's see. So let's draw it this way. And remember what you were responsible for was the electric field along these two directions. That's on the equation sheet. What's the electric field here, and what's the electric field here? Okay. And remember, let's see, to the side, it was very similar equations, and it points down to the side, and it points up along that axis, E. And the formulas reflect that, right? If you write the formula, it doesn't have the two. E here, it's on the formula sheet, is minus K moment over r cubed, right, like that. So it's negative. It's down because there's a negative sign there because it's in terms of the direction of the moment, right? It's the opposite to the direction of the moment. If we flip this the other way, this would flip the other way. All right, so minus k moment over r cubed. You could almost remember that because this is like charge times r, and it looks just like a field equation from Coulomb's law, except we have a moment here, so we need one more r there. And it's negative. Here, E, I think it's just half, twice that, 2k moment over r cubed on the equation sheet. So that's why I'm not writing it big and pretty. It's on the equation sheet. So you want to be able to use those. You want to remember how to use those, okay? And then also on the equation sheet is torques, right? We talked about it. We had homeworks about it. How do you know which way the dipole moment goes? The problem will either define it for you or show you. You look at it and you say the negative here and the positive there. Therefore, the dipole moment is always negative to positive. I don't remember if the equation sheet defines the dipole moment and tells you that. I don't think it does. Yeah, it says the dipole moment is P equals Q. P vector is QS vector. It says this. You have to know that an S vector goes from negative to positive by definition. All right, so let's say the other important thing then that we talked about, I think I have a problem about all this eventually, is this. So say you've got a dipole moment in here, and it's at some angle with a field, theta, right? Sitting there at some angle. And so an example problem would be, this would be kind of a not so hard one, is rotates which way? Which way? So this would be one you wouldn't really get with math. You would probably just get this by thinking about forces. So it's about a dipole, but it's really just an F equals QE problem. Right? So which way do you think that thing is going to rotate? Or maybe you think it's not going to rotate. Maybe you think it's just going to sit there. Think about that while I answer these. Can you explain why the electric field is negative to the right of the dipole? We explained it last time. It takes too long. Oh, field, vector sum, like that. Think of the vector sum of the field of these two charges, and it'll look like that. And that's why it points down. Can you repeat why the equation has a negative? Yeah, it just did. Would Q be positive or negative charge value? Q is the magnitude. So in this equation, Q is here, put bars on it. I'll put bars on it on the equation sheet. There is a negative charge and a positive charge. The dipole moment is the magnitude of that charge. It's irrelevant. They're the same magnitude times S. So you don't use the charge to invert the direction. That's not how it works. Magnitude. Do we have to know pre-rec stuff like a charge moving electric field? A charge moving electric field and velocity, yeah, it's a pre-rec. What? I mean, we didn't make a lot on kinematics, but here's some kinematics. Which way would this rotate? Let's get back to this. Let's see. The field, I'm sorry, I didn't really draw it that obviously, is down. Right, so in this case, this would feel a force down, F equals QE, positive Q times the electric field down. This is on the equation sheet. All right, so this would go down. This would feel a force this way. So it must be, what? I wrote clockwise, but it's very clearly counterclockwise. Oh, now I got to edit my notes and re-upload them. Oh, my God. Okay. Unless I'm like having an hallucination. No, that's definitely counterclockwise. I think I looked at my clock and it was backwards. I was behind my clock. Stay in front of your clocks, everybody. Okay, now let's look at the value. How would you calculate the torque? What if we asked you for an actual torque, like a number? Panic time. What would you do? You'd go to the equation sheet. Oh, my God. Right? And, oh, it's got to recognize my face. It's really me. And you'd say, let me look up, oh, we have an equation for that. If you have this thing in the thing, then you know that the torque from last semester is P times E times the sine of the angle between them. So that's also on the equation sheet. So there, P, Q times S, that separation might be given to you, whatever. The angle might be given, or you might have to figure it out, who knows. And the E field, this is in a uniform field. I should probably add a note, uniform. I mean, it's true also non-uniform, depends on how big the dipole is and stuff we didn't do. Okay. Oh yeah, so an example then, a question would be, for this one, and it's based on a formula that is on the sheet also. In addition to the torque, we know that the energy of a dipole in a thing is minus P E cosine theta. Okay, so you can think about the forces on that little dipole in the uniform field, or you can think about the energy of the dipole in a uniform field. So a simple question, not simple, I'm saying it's simple, I mean it's easy to ask, is draw in the minimum U orientation. So if we gave you that, now draw it in the minimum orientation. That gives you the least energy, the least potential energy. Oh, I answer a few of these. Oh my God. What if the plus and minus charge magnitudes of the dipole aren't equal? They will always be equal. The definition of a dipole is that they will be equal. Yeah, we answered that one. So they will always be equal, unless it's a certain special class where a certain special professor writes them who likes to make them very hard. But that isn't this class. Why does the electric field go down on the torque problem? Because I made it do that. Right? So we didn't specify where that field is coming from. We just said there is a field pointing down. It's not being generated by the dipole. So the problem would say a dipole moment is sitting in a uniform field. Let's think, what would it take to make that field? This wooden plank would have to be a positive plane, and this wooden plank would be a negative plane. That's one way you could make that field. Right? Let's see. If the dipole, oh yeah, this is a good question. I found one. I found a good one. If the where is angle 0 degrees in this example? Yes, I didn't get to that. So like here, we're saying torque is PE sine theta. It's the angle between the P vector and the E vector. Right. So that's why I drew the angle there, because the P vector is from minus to plus. Right? There's P and there's E. Right? So I drew theta in the wrong place. This is why I don't crank out an exam solution at the last minute and put it online and confuse everybody, right? I meant to draw theta there. There you go. Okay. Let's see. Oh, good Lord. How do you find theta? Energy equation. Same thing. It's between P and E, right? Blah, 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 blah. So in the end, there's 2 minute answer. If the field was flipped face up, I don't know what face up means. It's not a mathematical statement. Is the torque for just one of the charges on the dipole or both? We multiply by 2? No. The dipole is just one thing. This is the dipole. Nothing is multiplied by 2. When you define P, you don't multiply it by 2 because there's 2 charges. When you get the torque, you don't multiply it by 2. When you get the energy, you don't multiply it by 2. It is an object. If we were treating it as 2 different things, we'd say it's 2 charges connected with a boba straw. Oh, wait, that's what we said. No, it's just a dipole. It's one object. Okay? Usually, when you're treating it in chemistry, it's a molecule, so you treat it as one thing. Okay. All right. Flip to go upward. Yes, everything would change around. So let's draw this. And the minimum energy orientation is basically, you don't even have to use equations, right? You could say, when is that going? Well, you could do it with math or you could do it with intuition. Math. When is this going to be minimum at what angle? 0. Because when cosine 0 is 1, you get a negative number. If it were 90, you'd get 0. If it were negative 180, this would be a negative 1 times negative 1 is positive. So it's clearly when theta is 0. So you would just have to draw it like this. E, it must be that the dipole points down, which is from minus to plus. There you go. That's when theta equals 0. So theta went from this big angle up here all the way down to 0 down there. Okay. So here theta equals 0. And if you wanted to do it physically, you could say, well, I know I'm at the minimum energy when this has gone as far down in potential as it can, right, along the field, and this has gone as far down in potential also. Like these are at their minimum electrical potential, or potential energy, if you want to think of it that way, in these positions. But I would just go with that, if that makes you feel better. Okay? So a dipole likes to align with an electric field, is the main thing. Okay, would max U be if the dipole is perpendicular to the field? Nope, not quite. Right? If we said what is maximum energy, you could get this all the way up to plus PE, because that would be 180. So here's max, and you would just have to flip it the other way. There's max. What is special about perpendicular? What is special about this? Nothing. There's nothing special about that. There's nothing special about any of this. Okay, so that's just sort of a bunch of little mini problems to remind you. You do need to know a little bit about dipole moments, but all that means is you need to know how to use these equations. You don't have to rederive any of this stuff. You just have to know how to figure out, oh, that's the field, and I do have to be able to think a little bit about torques and energies. But did we really have to use this equation to answer that question? No. We just thought physically about the forces. This one, we kind of needed the equation, you know. Why is it useful to know what S points from negative to positive? Why is it useful to know that S? Because that's how you're going to know if it's aligned or not aligned. That is, like to use these equations, theta is the angle between P and E. So if you don't know which way to make S, you're going to get theta wrong by 180 degrees, possibly. Okay. The whole exam is not about the dipole moment. Okay. I'm not sure you actually have to be able to get the S vector right for any of the questions. I can't remember. But it would be wise to understand the dipole moment. All right. Let's see. Remember the dipoles. And then finally, I have 2 circuits. Oh, good. This is taking a long time. Good. Man, problems take forever. Oh, I don't have my thing. Oh, can't erase anything. Oh, I got to go to Target and buy more towels. Okay. All right. Someday, Rice is asking you for money. You think, I'm going to donate some money so Hafner can go buy another set of towels. Okay, now, the next thing, can you do this? Bend the circuits in your mind. Right. So So somebody asked on the balance of this thing, right, it's all fields and potentials, right? There's no circuits on it. Yes, there are circuits on it. So if you look at the equation sheet, it is very uniformly balanced, I would say, through everything. So there's no certain topic that's on there and certain topic that isn't. It's pretty balanced. So what I mean by this is sometimes a circuit will be laid out in a way where it's not just obvious what's in series and parallel. Okay? And we don't do that just to turn it into an IQ test. Because to be honest, if we made this an IQ test, you guys would do better. Y'all are so smart, right? So that's not the point. The point is to think about series and parallel and where circuits break and the fact that wires are all at the same potential. So there is actually some physical insight into doing these kinds of problems. So let's do one real quick. Here's one. And all we got to do is turn it into a diamond, and everybody freaks out. I think diamonds are pretty. Oh my God, I can hear you cringing as I speak. I mean, more than usual. So here we go, like this. Oh my God, R, 2R, 3R, and 4R. Oh, are we miserable enough yet? Let's make it worse. Oh my God. What are we going to do? So before you, and look, the capacitor like wires aren't even like level. Wow. You guys are screwed on this one. Make it stop, please. No, we're not going to make it stop, please. I had this idea that what if Whitman knew about the magnetic field, the body magnetic? There's some serious like alt-fic poetry there. That may be how I spend my whole weekend. I'm not sure. Okay. So first thing I would do is kind of redraw it. Okay? Just think, how might this look more rectilinear? I mean, what's going on here? These things are at 45 degrees. So what? This is all at the same potential. It doesn't matter that this is at 45 degrees. This could have a bar, and they could be like that. The direction doesn't matter. Just make it like that. Make it rectilinear. Resistor, resistor. And if there's a weird element, just don't do that element. Put it in later. So we're coming along. I don't know what to do with that. Let's ignore it for now. We're just coming along. We hit another resistor. Did anything exciting happen? No. We just hit another resistor. So let's put another resistor. We'll deal with the capacitor later. Here, same thing. We just hit another resistor. That's all. Now, what about here? Oh, it's coming into a diamond, and they're at 45 degrees. So what? Right? It could do this. It doesn't have to be a diamond. So we just make it like that. Right? See how much nicer that looks? That doesn't look so bad. R, 2R, 3R, 4R. R, 2R, 3R, 4R. And now let's think, where are we going to put that stupid capacitor? So you just look, well, it's between, on one side, it's between R and 4R, and the other side, well, it just goes across the middle. Okay, so now it's at least rectilinear. The capacitor may still bother you, but we haven't even asked what the question is yet. Maybe the question will make it not so bad. How do you calculate the potential of a wire between two resistors? I don't know. I think that comes up in this question. Okay. So the question here, first question, what is the current in this circuit? And usually we'll say the current through one resistor, the current through another resistor. Here I just mean the current, the total current coming out of the battery. All right. Okay. So let's say current, total current. What is the total current? Well, it's just a bunch of resistors in series and parallel, but there's a capacitor there. So what are we going to do about that capacitor? Well, usually the capacitor problems like the RC circuits have a switch, and we asked, it has been hooked up for a long time, or did the switch just close? Well, there is no switch. So it's probably been hooked up for a long time. I'm going to print the exams tonight. So it'll be been hooked up for at least 24 hours, right? So I would say this is a case where it's hooked up for a long time. Now, how do we treat a capacitor that is hooked up for a long time? We put a ring on it. No, what do? We treat it like an open wire. The C is an open wire. Okay? And when I say it's an open wire, just erase it. Okay, just do the problem like this. It's not affecting the circuit. It's just experiencing the circuit. Oh, that sounds experiential learning. There it is. There we go. There's the circuit. In terms of resistors and currents, the capacitor is doing nothing. It's an open circuit. Here, I'll draw little wires Here it is. It's like the evolving nubs of the capacitor there. So we could solve that pretty fast if you know about how to add those up. Then you start doing, you either do it in your head or you just kind of figure it out with math. If I was going to do it with a picture, I'd say, well, this is 2 branches. These 2 we're just adding, right? 2 resistors in series, 5 ohms. Or 5R. Oh, my God. Okay. 4R plus 1R, 5R. 2R plus 3R, 5R. Yes. If I go fast enough, you don't have time to ask questions. All right, so then the second one I wouldn't even draw. I'd say, if you want to be able to go fast, 2 identical resistors in parallel have half the resistance. Right, 1 over 5 plus 1 over 5 is 2 over 5. Flip it back over, it's 5 over 2. So eventually you'll get good at that, and you can do it real fast. And you'll say that then the EMF times the I times the R equivalent. REQ means the equivalent resistance of the entire circuit, which we now know is 5 over 2R. Right, so I is the EMF over 5 over 2R, also known as 2/5 EMF over R. Oh, good, that's what I got. Let's see. Could you repeat why the capacitor isn't important here? It's completely charged up. So, I mean, I would just memorize that if it's a long time after a switch is thrown, the capacitor acts like an open circuit. The reason is, if there's a potential difference across the capacitor, like it looks like there is here, it's going to build up charge, all right? It's eventually going to build up so much charge that this is at some voltage difference equal to what it would be if it weren't there, right? It's going to build up charge until the current stops flowing, and this is just at that potential. So then the current's just going to go this way. Because eventually, if this potential is the same as this potential, then current won't go that way. It'll go this way. So, I mean, the physics of it, that's about as clear as I could say it. I could probably do it better if we spent a lot of time on it. But basically, it acts like an open circuit because it's built up all the charge it can take. Do we need know how to do circuits with 2 batteries? That's a sensitive subject. I don't think it's a critical skill. Okay, so the, I is 2/5 E over R is what we decided. But let's see the harder part of this circuit. Yeah, let's see. Do we need to know how to do circuit with 2 batteries? What if the capacitor was if it was not fully charged? If it's not fully charged, this is an RC circuit, and I have an RC circuit coming up. So let's just keep going so that I can get to the RC circuit. All right. All right. All right. Okay. Okay, so the second part of this question, a good one would be, what is the charge on the capacitor? Right. Yes, that's what we're about to do. What is the maximum potential difference you can get across that capacitor? Is that on the battery or the minus potential? Yeah, so that's what we're asking right now. What charge do you get on this capacitor? Okay, so the way to figure these out is you say, actually, there was a capacitor there, and there's just no current flowing to it. So you say the charge on a capacitor, I know, it's Q is C times the delta V on the capacitor. So now you have to go with physics and say, okay, what is delta V on the capacitor? It's the difference between the potential here and the potential here. So you got to go back to the resistor circuit and say, what's the potential of those wires, right? So you'd look at it and you'd say, okay, let's look at it again. There's the EMF. We got 2 resistors here and 2 resistors here. You can sort of go about it with a lot of equations, or you could go about it intuitively. And we don't really have time for a lot of equations. Let me do it intuitively, and I'll tell you what equations you would use. Okay? So you could first calculate the total current. We did that. 2/5 EMF over R. E over R is flowing like that. Right? You could then figure out how does that current split here. Right? If you did a whole analysis and the delta V and everything, how does that split here? And then you could say, how much potential drop do I get across this resistor? And how much do I get across this resistor? It's different, right? R, 2R, 3R, 4R. Right? The potential drop across this one and this one will be different because it's a different amount of current. Actually, it's the same current. Is going to go into each side. Okay? So you could do like a numerical analysis of how the current splits there and do those drops. A slightly quicker way is to look at it and realize, well, it's a voltage divider. Anytime you have two resistors in series and you want to know which one is, what's the voltage across each, we call that a voltage divider. They share the voltage and it drops with proportion of how big they are in resistance. Right? So let's zoom in on this square and show you what I mean. If you're going to use a voltage divider, you need to know what the total drop is first. Well, you do know the total drop. This wire is all at E, and this wire is all at 0, 0, 0. If you say the positive terminal is at E and the negative terminal is at 0, then the drop across the whole branch is E, the EMF E. So you should be able to recognize that. So you have EMF E over here and 0 here. And you just got to think, how do they drop? Right? So R, 2R, 3R, 4R. So the whole drop E, it drops proportional to how much resistance there is. So it's all dropping across 5 Rs, but this one drops 4 of them and this drops 1 of them. So basically you get 4/5 of your drop here, 4/5 EMF, and you get 1/5 of your drop there. Right? So basically this is at 4/5 EMF. Right? We dropped 20% down and then we dropped 80% down. Right? That's how the voltage divider would work. The voltage divider formula would be delta V is R1 over R1 plus R2. Delta V over 1, delta V total. I mean, that would be the formula. It's just the ratio, right, of the resistor you're thinking about to the total. So that's why we dropped 1/5 of the voltage here. The delta V is 1/5. It went 1/5 below EMF, so that's why the potential is at 4/5 relative to down here. So hopefully everybody sees that. It dropped 20%. Now what about this one? Drops 40%, right? It dropped delta V 2/5 EMF. So that point is at 3/5 EMF. So the delta V of the capacitor is 1/5 the EMF, right? This side is at 4/5 E, this side's at 3/5 E. Right? What's the difference? 1/5 EMF. So what's the charge? 1/5 EMF times C. So that would be the potential. And that's a lot of people were asking basically that question. How would you get that potential difference? You're finding the potential of this wire relative to ground, relative to the negative side of the battery, and you're doing it based on how things drop. Okay? If you're wondering about the time dependence of this equation, we wouldn't do a time dependence on this because we're just doing the simple RCs where it's a resistor and a capacitor in series. We could maybe have two resistors in series with a capacitor, but this would have a more complicated RC behavior that we don't do. That's like engineering class, okay? Okay, do we want to power through the RC question or do the break? I can't decide. I'm worried if I don't know. Maybe we just don't want to do a break. Okay, I feel like a chill has come over the classroom. Oh. How does a grounded circuit differ from a regular circuit? They're all grounded. Why does it mean to conceptually when a switch immediately closes in a circuit with a capacitor? So if there were a switch in this thing and this immediately closed, that would be a short. So we're going to do that in the next problem. Let's just power through this one, take the 5-minute break, and then just do one magnetism question. Let's power through. There we go. While we're in the RC zone here. All right. Okay. A, B, right, R. Where's the capacitor? Here it is. La. Yes, this is the one. Here we go. EMF. Right. So question 1, here we go. So here's an RC circuit, and we have a switch. A switch is your hint that there's going to be time dependence. We're going to open it, we're going to close it, we're going to think about how it changes, etc. So, if we wanted to give you a first warm-up question, just to get you going and not have to think, could you move the board up behind to the top, please? I don't know what you mean. I can't reach it if I draw it too high. You can come move it. I don't know what you mean. Okay. Is A or B the charging circuit? So first, I hope you can recognize which position of the switch is going to actually charge that capacitor up. It's the one connected to the battery. Right? A. Right. So if it's touching B, there's nothing going to put any charge. It's just a capacitor and 2 resistors. Remember, if one side of an element or a battery is touching nothing, it's just out. Nothing's happening. Okay? So when this touches up here, we clearly could have charge flowing from the battery to the capacitor. When it's down here, then it's just this loop. This looks exciting and everything, but it's over. Right? It stopped at A. So that's just big A. So that was sort of the warm-up there. And then you could say 2 is charge or discharge faster. These are like if we did a multiple choice RC problem. You could say charge is faster, discharge is faster, they're the same speed. There's no answer. I need to know what R is. You could say all kinds of things. So this would be a question where we're not probing, can you plug into those equations and figure out where the charge is at, how long does it take to get to half the time, kind of like the homework. This would be, do you really understand what the time constant is? Because remember, all this charge, discharge stuff, both of them, Q is Q naught, 1 minus e to the minus t over RC, right? And then discharge is Q equals Q naught, e to the minus t over RC. They both depend on the time constant RC, right? Now, one thing not to get mixed up about is this means whatever RC is in the circuit. If we're going to apply these ideas, we have to put in the actual value of R, okay? So let's look. When this thing is charging, the current flows through this loop. It doesn't flow here because this isn't connected, right? We're up here now. We're in A. So it's C, and then what is R? In this case, R is R over 2, right? 2 resistors in parallel. So when it's at A, the time constant, we write it as tau sometimes. We could just say T over tau if we wanted to. It's 1/2 R, that's the resistance, times C. Right. But then if we did B, what if we switch it down to B? How fast is it going to discharge? Tau, the time constant, is 2R, because they're in series, 2RC. Oh, yes. And then you got to think, wait, what does faster mean? Faster means the one with a shorter time constant. Or if you really needed to do it, you could plot it for yourself. Which one is getting to some value more quickly? It's the one with the shorter time constant is a faster one. So you would also have to know that tau is in units of seconds. Tau isn't like inverse seconds. Tau is seconds. So, of course, this one. The one with a half in front of it would be the shorter one. So this circuit will charge faster than it discharges. By how much? 4, depending on what we ask. Another question, if we want to get this one a little more quantitative, we could say 3. Faster is one question. Which has the larger initial current? What? Yes, this is verging on calculus based. Okay, are the current equations on the formula sheet? Good question. I don't remember. Are the current equations on the formula sheet? No, they are not. Whoa, you're going to have to take a derivative, right? So first of all, what does that even mean, the initial current? Well, if you think about it, if this thing's uncharged and you switch it, you immediately start charging it. So some current flows at the beginning, but once it's charged up, the current stops, right? So you would think, okay, there's some initial current. And then once it's all charged up, the current is stopped. But if you flip it down, then as the thing discharges, some current's going to flow the other way. So that'll have some initial current as well. So in an exam, I'd be more careful and say magnitude of the initial current, so you don't worry about the sign, right? Okay, so somebody asked an important question. These look the same, so that's the difference. So here I'm saying the total REQ of the circuit times C. The total REQ of the circuit times C. Here I've plugged in for these individual circuits. So ideally I would have called these a little r or something, but then everybody would have had a heart attack. Okay? So this is R equivalent, and here I've plugged it in. R equivalent, I've plugged it in. Okay, so we want to know what are the currents here. Well, you know that current, so this would be the tricky calculus-based part, is a time rate of change of the charge. I'm sure this is in the book, and I'm sure we talked about it. That's a constant, so that derivative is nothing. It's a negative, but when you take a negative here, the negatives cancel, and it's Q naught, and it looks like it's over RC, e to the minus t over RC. So that is when you charge, right? That's the current. So you can see I naught is Q over RC. Well, when you charge, there's a half down there, right? So equivalent again. I'm just taking the derivative of the equivalent one. And here it would be the same thing, actually. If I take this derivative, it's just Q naught, let's see, I, Q naught, the derivative you bring out of minus 1 over RC, R equivalent C, minus, if you want, e to the minus t over RC, equivalent, right? So if you then took these and said, okay, this clearly with my initial current is always Q naught over RC, Q naught over RC. They have the same Q naught, charged it up, discharged it, same Q naught. So you got to put the RC in the bottom. So the one with the smaller RC in the bottom will have the larger initial current. Right? The one with the bigger RC in the bottom will have the smaller initial current. So larger is this one again. And then you step back and say, does this make sense? Yeah. They have the same initial charge, and this circuit is dumping it faster. So yeah, the one that's going to dump it faster is probably going to have the bigger initial current, right? Because current is the flow of charge. So the faster one wins both those answers. So that is sort of an intuitive RC problem, not a quantitative solve something in seconds RC problem. Okay, this is going to be painful, but let's take the break and then talk about the magnetic field. Just a little fun part of the magnetic field. I might electrocute myself. It'll be fun. You never know. Yes. Okay, we're going to talk a little bit, just for, 14 minutes of magnetic field excitement. All right. So, how does it start? Yes, so I need my blankie. All right. There we go. So last time I gave you this loosey-goosey, kind of deranged introduction to the magnetic field. I actually don't really remember it. It was sort of a fever dream kind of a thing. But just to give you the idea of the magnetic field, it depends on charges moving. So there's sort of an analogy to the electric field. Electric field is forces of charges. Magnetic field is the force of charges moving. And you're used to thinking of the, You're used to thinking of the magnetic field in terms of these magnetic materials. But really, those are magnetic because there's little atomic charges moving. So it's all about charges moving. So we want to figure out then the simplest, most fundamental thing to do is to think about the magnetic field created by a current in a wire. That's the basic thing. So we'll say current creates a magnetic field. Because current, we know, is moving charge. I is dq dt. And this is called the Biot-Savart Law. Okay? And actually, the thing we're about to write, let's go and just draw it. So here is a wire. It doesn't have to be a straight wire. Any wire with current flowing through it creates a magnetic field. So let's say there's a current, little I, flowing through this wire, like that. And let's say there's a point P out here. And we want to know the magnetic field at P. Okay? So the fact that currents create a magnetic field wasn't known for a long time. Magnetism was discovered based on, these special rocks that seem to align with the magnetic field of the Earth, with something about the Earth and always point the right way. That's why we call the poles north and south. And they seemed to interact with each other, but there was no idea that it was related to electricity. Electricity was batteries and rubbing cats and all that. They didn't know these were related. So the discovery that they were related actually occurred during a demo in a lecture demonstration by Ørsted. So you never know, we might discover something while we're messing around here. We're more likely to discover some psychological thing. But who knows? Who knows what we might discover? So what we're going to do is this. These are a bunch of compasses, and they're all pointing that way because that's north. And this is a wire carrying current. And to really see the effect, you need a lot of current. So in electrostatics, I'm pretty brave because it's just going to hurt, right? A shock from an electrostatic device, lots of voltage, but not enough current to really hurt you, or enough charge and current to kill you. This, you could easily kill yourself with this. So you'll watch, I get much more gentle around these demos. I'm like, okay, now we're going to turn it on. No current yet, but when I throw the medieval switch here, the current is going to start to move, and then you can see maybe the magnets will start to move. So I'm Ørsted. Hey, how's it going? Hey, anybody get their leech shots today? Okay, well, here we go. Let me send some current down this. Whoa, what happened to those compasses? Look at that. That must have been a coincidence. Oh, it must still be a coincidence. Go get the philosophy department here. What if I go this way? Oh, they moved again. Right? So there's something about a moving current that is affecting these magnets. And if I leave it on long enough, it'll smoke. Okay, we shouldn't make it smoke. Okay? So that's what we're seeing is this current is creating a magnetic field, and the magnetic field is bigger than the Earth's magnetic field. So it's making those little magnets turn. Okay? So here's the formula to get the B field from this current. Oh, you're going to hate it. You're going to hate it so much. First of all, it's a differential definition. Why is it differential? Because you... Yes, I love the smell of barbecued current in the morning here. It's a differential definition because you can't have a point current. Right? You can have a point charge, but how do you have a point current? Here, here's a little teeny piece of wire with a current in it. Well, how could that possibly happen? It's got to be a loop. It's got to be hooked up to a battery. You can't make a point current. So therefore, to get the B field, we have to think of a wire as a bunch of little point currents, little differential currents, and add up all their effects to get the B field somewhere. I know, it sucks, yeah. So the B field at P, the differential element to the sum of the B field at P is due to this little piece of the current ds. So we're going to integrate along the current, the wire with the current like that to get it. Constants, mu naught over 4. That's my mu. It's horrible. Let me try again. Mu naught. There we go. Over 4 pi. The current. Okay, I can handle that. That's a constant. ds. Okay. ds is just along the wire. Cross r. What? Oh my God. Where's r? r is from the ds to the point P. Oh, yes. There's r. And it's a cross product in the differential. Wow. That's actual vector calculus over the magnitude of r squared. All right, this is Biot-Savart law right here. And let's define a few things. Well, I don't want to define all these because we'll waste all our time. Let's define the one we don't know. Mu naught is the permeability of free space. Oh, that's going to be in my Whitman poem for sure. Free space. All right. And it's got a convenient value 4 pi times 10 to the minus, I want to say 7. I am correct. Newton per ampere squared, I think, is the unit. So that's like your epsilon naught or your k. 4 pi times 10 to the minus 7. ds is hard to see, but ds is that, that little differential element. These are all ds's here. All right, there you go. ds's. R is from here to here. R is from the ds to the p. I'll go ahead and write that one too, because that's a little tricky. R is from ds to p. Right? And ds, I'll go ahead and define. ds is an element of the wire. Okay. So if you're doing a field theory heavy electricity magnetism course, we use that equation and do the integrals to get the fields of different geometries. Okay? I have the notes to do it for a straight wire. And I think we'll do it. But first, we have to talk about that cross product. I think a better use of our time today, and we might get to the integral, I don't know, but a good use of our time today would be to think about this and maybe get this in your head so that over the weekend and over Willy Week, the cross product will just be building in your head. So let's do one thing on the cross product here. Here we go. Let's do it over here. This board stinks. Cross product. It involves something we all love called the right-hand rule. So I'm going to tell you all the secrets of the right-hand rule. Okay, the right-hand rule. Let's see. Right-hand rules. There's more than one. Right-hand rules. If you've been watching very carefully and hanging on my every word and gesture, you may occasionally see me draw a Cartesian system and go, okay, I'm doing the right-hand rule. I'm like, the wizards that don't have to do this. I do the right-hand rule like this. Okay, we're good. Okay, so you'll start your right-hand rule like this. Okay, that's what you're about to do. Here we go. So rule number 1 of the right-hand rule is use your right hand. Okay, more than once I've had somebody in my office, I can't get this problem to work. It's always negative. I'm like, yeah, that's your left hand. Okay, very smart students we admit to this university. If you don't know what your left hand is, it's okay. If you do this, the one that makes an L is your left hand. Okay, I told that to George, and he said, they both make an L. I'm like, you little shit, I swear to God. I'll kill this kid. Okay. So now, you always use your right hand. You use the right hand rule in different cases. Okay, so right now we're doing a cross product. So let's say two vectors A cross B, right? Because that's what we have here. We have ds crossed with r. Okay, cross product A cross B. Fingers along A. Here we go. Sub-bullet star. Fingers along A. And this is the part everybody hates. Okay, curl them to B. This gets into physiology. And then your thumb is C. Okay? So let's take a cross product of A this way and B that way. A cross B, and we've got to figure out which way is C. We're saying C equals A cross B in all these cases. Okay, this is how we get the directions of things in magnetism. Because remember I said magnetism is weird, it's loopy. Everything in magnetism, the fields and the velocities this way, and everything's always to the side. It's inherently always in 3D. That's why we have to do this. In electricity, electric fields, everything pushes along the field. So it's easy to just do things in 2D. Magnetic things are all inherently 3D. Okay? So let's do the first one. I said the fingers along A. Okay? Here, my fingers are along A. But I've set it up to where it's definitely going to work well. Let's make it hard. What if I walked up to it like this and said, here, my fingers are along A. And now it says, curl them to B. And it's like, I can't, right? So it's actually the physiology of your hand is part of doing the right-hand rule. Okay? This is not curling them towards B. This is curling them away from B. I want to curl them towards B. You have to turn your wrist. See, the thing with right-hand rule is you put your fingers along A, but you got to get your wrist the right way, right? And it's your forearm you're curling. When the book says turn your wrist, hold your forearm still and try to turn your wrist. You can't actually turn your wrist. You can only turn your forearm, okay? So put your fingers along and turn it, your forearm, until it's actually going to go along B. This is the way that goes along B. Only this way. Yes. So which way is a cross product? This way. And also important to know, in vector notation, X means into the board. That's like an arrow shooting away from you, okay? Into the board. A cross B into the board. So the reason you'll see me drawing axes and doing this is because we always have X cross Y is always a Z direction by definition. So if you draw X and Y and you want to draw Z, it's got to be that x cross y is in z. Let's do another one. Let's put A, let's put A like that. Whoa, what is that? That's out of the board. That's a vector pointing out of the board. And let's put B like this. A cross B. Oh, let's see. A. No, that's no good. That's no good. I can't do it. Oh, like this. No, like this. Sometimes you have to go into the board and stick out of the board. It's hard. Okay, sometimes you have to do this and say, okay, if I was like this, that way, and it's this way. All right, so it's perpendicular to B. It'll always be the case that the cross product C will be perpendicular to both A and B. So basically, A and B make a plane, and C is always perpendicular to it. You could also ask, do things have to be perpendicular? No. The first two vectors don't have to be perpendicular. Here's another fun one here. Let's make A this way, and let's make B that way. A cross B. Which way is it? A cross B. It's out of the board. C out of the board. These aren't perpendicular, but C is perpendicular to both of them. Right? So it works. All right, final one. Let's go over here and say which way is the magnetic field. And we'll have to do the integral on Tuesday. I'm sorry. ds is along ds crossed with r out. So the B field due to this wire is out of the board. So that would let us just say out and get rid of the cross product. Right? But we'll do that next time. Okay, good luck Friday.